All right, good morning. It's time to start. So today we are going to cover unrestricted grammars. So just like we saw um, right linear or left linear grammars, which are called regular grammars, which have the same power as DFA and FA. In other words, they can generate the regular languages. And then we saw, of course, context-free grammars, which have the same power as MPDA. Today, we're going to look at unrestricted grammars and show that they are equivalent to Turing machines. So let's define what they are. And in a sense, we already did that, because when we define grammars at the beginning, that's exactly what we defined. So a grammar, as usual, has four components, right? The B, T, and S are the usual, right? Variables, terminals, the alphabet on which the strings generated by the grammar belong, and then P are the productions. So what distinguishes the various types of grammars is just the power of the production, right? So how general are the productions? So for unrestricted grammars, well, the productions are unrestricted in the sense that the only restrictions they have is that they must contain a variable on the left-hand side. So we can write it as this. Well, actually, it's going to be a finite subset of B union T star V B union T star cross V union T star. So all that says is simply that they map a string of variables and terminals into a string of variable and terminals. This one can be epsilon. This one, the left-hand side, must have at least one variable, right? So of course, context-free grammars are of that type, but here in addition, we can have a context, right? Okay, so and as usual, we define L of G to be equal to the W such that from S, in some number of steps, according to the grammar, we can generate W, and W is just made of terminals. Okay? That's what a grammar does. Okay? All right, so let's have some fun and let's use unrestricted grammars to generate some languages which are definitely not context-free. Right? So for example, I'm going to see a little bit how the way unrestricted grammars operate is a little bit like as if they had the tape, in a sense. The sentential form that they operate on is very close to the contents of the tape of a Turing machine. So let's generate L equal W in ABC star such that the number of A's is equal to a number of B's is equal to a number of C's, right? And we know that this is not context-free. We can do it if I have A's and B's, but I cannot do it if I have A's and B's and C's. Okay, so the grammar will have variables A, B, C, and S for the starting. A, B, C, uppercase, of course, they're variables. Then the alphabet on which I generate strings is, of course, little a, b, c. And of course, the starting symbol is S as usual. So now let's look at what the productions are. So where the productions are, S goes to A, B, C, uppercase, S, or epsilon. So let's just start with this, and then A goes to little a, B goes to little b, C goes to little c. Okay, there is more, right? But if we just had this, then what we would be able to generate is something like S generates A, B, C, S. In one more step, I can generate another ABC, for example. So I do ABC, ABC, S, and maybe one more, right? So I do ABC, 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 S. And then let's have S goes to epsilon. And so now I have ABC, ABC, ABC. Well, now if I have the A's, the B's, and the C's go to little a, little b, little c, I will generate 3 A's, 3 B's, and 3 C's. So the string is in the language. However, if that's all I can do, this is a regular language because all it can do is to generate ABC in order and then ABC again, ABC again. So this language would just be ABC star, which is a regular language since that's a regular expression. So what's missing between what I want to do and what I'm doing here is just that here the order of the A's and the B's and the C's is restricted to be always 1A, 1B, 1C, 1A, 1B, 1C, 1A, 1B, 1C. Well, unrestricted grammars can use context-sensitive type productions. So all I have to do is I can just swap the A's, the B's, and the C's in any order. And to do this, all I have to do is add something that says if AB changes into a BA. If I have a BA, change it into an AB. If I have a BC, change it into a CB, and so on, right? So I can do all the pairwise swaps. So now, obviously, if I have this, I can change this AB this way, and then the CB, and then this one in any order. And no matter what I swap, I will always still get the same number of A's and B's, right? And then when I'm tired, I just drop, or when I have exactly the order I want, right? I just change little a into little a, b into little b, and so on. And of course, as soon as I change these into a little a, then I won't be able to swap anymore because these swaps among variables, and that's fine. So obviously, it generates exactly what I want. Okay, so this idea of getting something close to what I want and then use swaps to get where I want is very common when I need to use unrestricted grammar. Any questions on this one? Okay. So let's do another one, which will show another type of trick that is very common in unrestricted grammars. I want to generate L, A to the 2 to the n is a natural number. In other words, I want to generate strings of A's whose length is the power of 2. So 2 to the 0 is A, right? So this is A to the A, and so on. Okay, all right. So again, this also, of course, is non-regular, non-context free. Here, I will have a grammar G where the variables are, we're going to use this bracketing trick quite a bit. So left bracket, right bracket, and then A, and then S, the starting symbol, and then this D, this mysterious D, which will be a doubler, right? To get this, we just need to keep doubling, right? So the D will let us double. Then, of course, the alphabet, the terminal is just A, the starting symbol is C, is S, and then we have our productions, and here, for the productions, I have, so S is just used to generate a bracketed A. So that's the only thing I can do at the beginning is from S, I generate bracket, A bracket. And I need this just because I need to have a starting symbol. I cannot have three starting symbols, right? But that's the only purpose of the S is just to get me the initial sentential form I want, which is bracket, A bracket. Then I have bracket can generate a bracket D. Sorry, a left bracket can generate a left bracket D. And the right bracket can generate just a right bracket. In other words, we're going to see that the left bracket generates these, and then the D's disappear when they hit the right bracket. But then, how does the doubler work? Well, if the doubler is close to a variable A, it will pass it, so I will switch the A and the D, but in doing so, I also double the A. So if I have the A, I do AAD. And that's the whole trick, right? And then, of course, at some point, I need to get rid of the left bracket, and I need to get rid of the right bracket, and that should be it. Well, no, of course, I also need to have uppercase A go to little a. See? So how does this work? So just like before, right, what I showed you is that I can generate the right strings. I also show that I don't generate bad strings. But that's the one thing which is very easy with unrestricted grammars is that it's pretty obvious normally to show that you will not be generating the bad strings. Okay, so in other words, I can just show you how it works when I want to generate a string in the language. So from S, the first thing and the only thing I can do is this. And then I can apply this one a few number of times, right? So, for example, I can do D, A, and then let's do it once more, D, D, A. Okay, so I apply left goes to left D, and then apply left goes to left D again. So now I have left D, D, A. Then we're going to apply these as much as we can, right? So DA, so I have left D, DA goes A, D. And then DA again here goes to, this DA goes to AAD, and then I still have the AD there. And then this DA again goes to AAD. So now I have AA, DA goes to AAD. Okay. And then, well, of course, I could generate more D's here again, right? But let's say I'm tired, right? And so all I have to do now is to do D right goes to just right. And then left can go to epsilon, right can go to epsilon, each of the A goes to little a. And I generate A to the 2 to the 2, 4 A's, right? Now, this idea of doubling, if you look very carefully, works for any power of 2, right? So if I generate 100 D's in the beginning, at the end I will have 2 to the 100 A's. Okay? And the interesting thing is that I cannot generate anything else, right? So obviously, I cannot generate a known power of 2 number of A's because either I don't generate a D, but if I generate a D, I need to get rid of it because it's just terminal. So I cannot have it, which is a variable. So for sure, every time I generate a D, I will double the number of A's I have. And then the only other thing is, well, I could apply the, this one I can apply anytime. But if I apply the D, if I apply the right bracket goes to epsilon, while I still have some D's, then those D's will not disappear. But that's okay. That just means that I should have applied first D right goes to right, and then the right goes to epsilon, and not this one first. But if I do that, then I don't generate a string. Yes, sorry, yes, you're right. This one there should be another D, and then I just remove one D at a time using that. Very good, thank you. So this is really in 2 steps. Thank you. So again, once you get this idea of doubling by essentially having these sweeps that move, in this case, just left to right, right? This is a very powerful idea, which is not that different from what a Turing machine can do. Then you can see why I am able to do powers of 2, and of course I can do powers of 3, right? If I want to do power of 3, all I have to do instead of generating the AAD, I generate AAAD, right? Okay. Let's generate another, which we have seen is not a context free. B A B A A B A A A B dot 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 B A to the N B. How do I describe this in English? Is runs of 1, 2, 3, 4 N B A's separated by 1 B, right? And we have seen that this is a very non context free, right? Because A7 is legal there only if I have A6 to the left and A8 to the right, or else nothing that was N was 7. Okay, so it's definitely a very context sensitive type, not context free language. Okay, so let's just write the productions here, right, to be a little faster. So from S, I can do A little b S or X. And then I have A little b goes to BA. A. So again, this is not a doubling, but it is a, again, as the A moves over the little b, it generates one little a. And then I want to be able to swap little a and big A. And then AX goes to just X. So X will be on the right. And then X eventually goes to little b, because I have one more b, then I have n plus 1 b's if I have n runs of a's. Okay. So how does this work? So let's do, again, from S, I can apply ABS 3 times. So I go, S goes to ABS, goes to AB, ABS, goes to AB, AB, ABS. Then I can apply S goes to X. So I get AB, 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 X. Okay. Then I can move my A's to the right. So in any order, right? So I can, like, change these, for example, I get A, B, A, so I change this, right? And then I have A, B, X. Then I can apply this one here. So I get BA, A, BA, A. So I've applied it here. ABX. And then, for example, I can do AB. So I go to BA, BA, A, B, X. And then here, I can swap the big A and the little a. So I get BA, BA, A, B, X. And I keep going. Right now I need to swap this one and so on. And eventually, if you keep going, you will see that in this case, I will be generating BA, BAA, BAA, with an AAAX, I believe, right? So then I apply 3 times AX goes to X, so I get rid of those. Then I go X goes to B, and I put a B, and I'm done. Okay? So again, when you use unrestricted grammars to generate something which is clearly not context-free, this idea of having, in the first case was, the A's, the B's, and the C variables can sweep back and forth to get the order you want. For the power of 2, or for this language, whatever you want to call it, I always have just a sweep from left to right, but I could do it from right to left if I had something different, right? So the point is that the idea of sweeping the sentential form is essential to get fancy languages, right? And in a sense, it's a little bit like the head of the Turing machine sweeping on the tape, right? One advantage, if you want, of context-free, of unrestricted grammars, is that when a Turing machine needs to do something like this, what does it need to do? Well, inserting a symbol on a tape means I need to shift everything by 1, right? And a Turing machine is very slow in doing that. Here, instead, in the sentential form, I just insert something, right? But again, that's just a speed issue, all right? Okay. So we have seen 3 examples of unrestricted grammars. They're kind of fun to use once you have these little tricks, right? Essentially, you have variables that can sweep, and then also you have these variables, right? The X at the end, or the bracket, that are essentially to determine that you are the left or right end of a sentential form, and you just get rid of those usually at the end. Okay? All right, so this kind of suggests that unrestricted grammars are very powerful, right? And maybe as powerful as Turing machines, which we're going to prove in a little bit today. But before doing that, recall that we have defined Turing machines not just as setters of languages or deciders of languages, but also as computers. Right? They can compute a function. And so we saw that a function is Turing computable if I can build a Turing machine that if I started with blank, the input blank, it would always end with blank, the output, the f, so input n would be f of n blank. Okay, so I can use those as computers or translators, right? Well, guess what? I can use grammars, unrestricted grammars, the same way, right? So we say that the function from sigma 0 star to sigma 1 star is grammatically computable, right? So you give me a string over sigma 0 in input, and I give you a string over sigma 1 in output. Okay? So this function is grammatically computable if and only if there is, well, an unrestricted grammar G equal, well, yeah, we can VT SP and 4 strings x, y, x prime, y prime in P union T star, in other words, strings made of variables or terminals, such that for all W in sigma 0 star, so if you give me the input W bracketed by X and Y, so from, and you consider this as a XWY. You consider this as the sentential form to start the grammar. So in this case, we don't start from S. The grammar in some number of steps will reach X prime F of W Y prime. Right? So in other words, think of the X and Y as the way to present the input. So I give you the input bracketed by X on the left and Y on the right, and so the input is W there. And think of X prime, Y prime as the way the grammar tells you, I'm done. Whenever there is X prime on the left, prefix, and prime on the right, suffix of a sentential form, then what's between them is the f of W. But that's not enough, right? Because a grammar can generate many strings, right? So what must also be true is that for all W prime different from f of W, XWY cannot generate x prime, w prime, y prime. In other words, not only the grammar computes, given it w, computes w and tells me it's there because it's bracketed, but no other string can be computed by the grammar with w in input bracketed by x prime, y prime. Okay? So otherwise it wouldn't be computing, right? It would be just giving many answers, right? I want one answer, right? And so that's what it means to be grammatically computable. So this is analogous to the Turing computable functions. And now we're going to essentially conclude by looking at two theorems, one in each direction, right? And that explains the fact that unrestricted grammars are as powerful as Turing machines. So, given a Turing machine n equal q sigma delta little s. So if you give me an arbitrary Turing machine, there exists an unrestricted grammar G V sigma union left bracket, right bracket, S P. Okay, so the alphabet of the grammar is sigma union these left and right brackets. Such that, and now we're gonna write essentially the grammar can simulate a Turing machine. Right? So if the Turing machine is in configuration state Q with U, A, V, so it's in state Q, and the tail contains UAV plus the infinite blanks, and the head is over this little a. So if from here, in some number of steps, the machine M can go to some state Q prime, U prime, right? So in other words, the machine can change from this configuration to this configuration in some number of steps. This is if and only if, which is important because the machine is deterministic, the grammar in a sense can do many things. So essentially this says really deterministic. If I start the grammar in the sentential form U, Q, A, B, the sentential form can change to U prime, Q prime, A prime, B prime, and so what does it mean? Again, the brackets are just there to show what the content of the tape is between them, right? Between the two brackets is the content of the tape that is relevant to the Turing machine. Now, the Turing machine has the state Q separate from the tape, right? It's not written on the tape, there's a state. The sentential form is the only thing the grammar has, but that's okay. We simply write Q to the left of where the head is, right? So UQAV means that the Turing machine is in state Q with the head over this A. To the left of the head, there is U, and to the right, there is V. Right? So it's pretty obvious that this describes this and vice versa. Right? So the theorem says that if you give me a Turing machine, I can build a grammar that does this, that simulates it, right? Because then, of course, if this Turing machine holds, then these will hold, and so on. Okay, so now we need to show that this grammar exists by saying what is V, S, and P, right? Then the alphabet, we already wrote it, okay? So V, the variables, are gonna be the states of the Turing machine plus the halting state, just because the halting state is not part of Q by definition, okay? And the starting symbol S, okay? Then we define what the productions are, right? So S is just S. We actually probably don't use it since we start from here. But we define what P is, right? So to define P, the productions must simulate the behavior of the machine, which means they must simulate the delta, right? So if delta QA is equal to PB, where B is a symbol. It's not left or right, right? This could be state P, left, right, or B is symbol. So when it is a symbol, then what does it mean? So in one step, all it would do is changes this A into a B. And so here we want to do the same. So simply we need to add the fact that QA can go to PB. All be in sigma. So that just shows how one production of the grammar can simulate the Turing machine changing a symbol on the tape. Then the alternative is that I have delta QA is equal to P right. So I go to state P and I move right. So I'm here, and so I will change there. So here what I need to do, I need to add, and when I move right, the Turing machine simply will find something under the tape for sure, right? Here I need to essentially guess, well, not guess, I need to say whatever is to the right of A, now I will have that under the head, right? So if I have Q, A, B, I will go to A, P, B, right? So the head is, so I'm in state Q with the head over the A, and I have a B to the right. If I move right, I'll have still the A there, but now my head I will be in, well, I will be in state P, and my head will be over the B. Okay. But also, I also need to add that if I am in QA bracket, what does it mean? It means that V is epsilon. Right? It means that the head is to the rightmost point. I have this infinite number of blanks to the right. So in this case, what do I do? Well, I will have the A to the left. I will be in state P. I will have a blank under the head. And then you can think of this right bracket as I have is the infinite number of blanks. Okay? Then if I have delta QA equal P left, so this is a little more complicated just because why? Well, because remember, V cannot be a number of blanks, right? Because if they were blanks, then it would be just part of the infinite number of blanks, so V would be just epsilon, right? So when I move left, I need to worry about hanging, and I need to worry about if what I have to the right of me is all blanks, I need to do something different. So normally I would just say, if I have B, Q, A, C, right? So if I am in state Q with A, and I have a B to the left and a C to the right, then I simply go to state P. I will have B under the head, and then I will still have the AC. And this is for all B in sigma and for all C in sigma. Union the right bracket. However, what if A is blank? I don't want to have blank bracket, right? Because again, blanks to the right are okay as long as they're not just blanks. So this is okay as long as C is not blank, because then of course A can be blank, doesn't matter, or A is not blank. Okay. If instead A is blank, so in this case we have BQ blank C. So if C is the right bracket, so what I need to say is what is BQ blank. So if I am in state Q with a blank under the head and then all blanks to the right, then what do I do? When I move left, I will go to state P with the B under the head, and then I just throw away the blank because that blank is part of the infinite run. Okay. And then finally, I can also hang, right? So if delta of QA is equal to PL, so still in this case, I need to worry about hanging, right? Falling off the tape. Now for a Turing machine, it just hangs, right? But for the grammar, it means I will have the left bracket under the head, right? So if I have left bracket QA, so here I would have to move left, but moving left means falling off the tape. So one way to represent this is just say, for example, this, where you throw away the state. Now, once you throw away this state, no production will be applicable, and so nothing can happen. Okay. So this is how you define the, given a Turing machine, you define the unrestricted grammar that behaves the same, simulates it, right? I should prove this, but actually it's fairly easy to prove because I'm not gonna do it, right? You can just think about it. But obviously you do it by induction, right? Because each movement, each of the possible moves of the Turing machine is exactly captured this way. And so if I can do one move, I can do any number of moves. So what we have just shown is that if you give me a Turing machine, I can build an unrestricted grammar that is just as powerful, right? It's just the same thing. So now we have to ask the question in the reverse. If you give me an unrestricted grammar, can you build a Turing machine that does the same thing, that assesses the same language that the grammar generates, right? So that's the other theorem. Given unrestricted grammar G equal BTSP, there exists a Turing machine M Q sigma delta S such that S can generate W if and only if M holds on W. Okay? So this is the language generated by the grammar, and this is the language accepted, not decided, accepted by a Turing machine. So to prove this, we can do it a very lazy way, which is just saying, well, I believe Turing's thesis. So given that Turing machines are the most powerful thing we can imagine, then of course they must be able to simulate a grammar. And yes, okay, sure, that's true. But if you want to do it in a little less lazy way, right, you can argue that if you're given the grammar, right, you know the production, the variable, let's say, let's start in simple. So one easy way is we build a Turing machine M, generates all strings over B, T, in lexicographic order. We know that a Turing machine can enumerate strings, right? Of course, we need to use dovetailing, right? So that's, again, is essential. So we'll generate all of them. Think of having a 2D infinite tape, for example, or a free tape, whatever, right? So it generates one string at a time on the tape in lexicographic order. And note, some of these will be completely junk, right? Will be arrow, 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 right? But some of them instead will be on the form, like S goes to something, goes to something, goes to something, goes to W, right? And it's, so these are, if these are correct sentential form, and if from S I can derive this sentential form, from this sentential form I can generate this sentential form, and then eventually I generate W. This is what? This is the derivation of the string W in the grammar. So a Turing machine is to do two things. One is to generate all strings that might or might not be syntactically correct as sentential form, right? For each of them, it does that in the seriographic order, which is dovetailing, right? So one at a time, in increasing length. For each of them, the Turing machine can certainly check whether this is a correct derivation, right? Because all it has to do, it has a finite number of productions, then it needs to verify, do I apply some production to go from S to this intentional form? Do I apply some production to go from here to here, from here to there, right? And if the answer is yes, and if, so the answer is yes, then this W is in the language, and then I hold, okay? The W is an input for the two, right? So I can just store the W in some, fourth tape, fifth tape, whatever. I can use multiple tapes, right? But essentially, the idea is instead of searching, behaving like the grammar does, I can be very brute force and just generate all strings that might be productions and just check, are they the production of W? If so, I hold on this thing, on W. If not, I keep running, right? I keep searching longer and longer. So again, the machine will hold if and only if W is in the language, because if W is in the language, eventually it will find a derivation of W by the grammar. Any questions? Okay, so what we have seen is that unrestricted grammars and Turing machines are equivalent, right? They talk about the same type 0 languages, they're called, right? All right. I'll see you on Wednesday.